Welcome to our top-tier security series. This is the 100-day IEC 6243 Mastery. Subscribe now and join the challenge. Let's master it together.
When most people think of a cyber attack, they picture stolen credit card numbers or leaked emails. But infiltrating an industrial environment produces a very different result. It can forcibly shut down a manufacturing line, poison a municipal water supply, or trigger a physical explosion on a factory floor. In 2010, the theoretical possibility of that kind of kinetic damage became a recorded reality with the deployment of a computer worm known as Stuxnet. Stuxnet infiltrated highly secured nuclear facilities. Once inside, it commanded the plant's massive centrifuges to spin at irregular, erratic speeds, physically tearing the heavy machinery apart from the inside out without a single conventional weapon ever being fired. The destruction of those centrifuges proved that malicious code could achieve the exact same outcome as a military airstrike. Industrial network vulnerabilities are national security threats. Back in the 1980s and 1990s, plant operators operated under a very specific assumption: isolation equals security. They relied on what is called an air gap. The idea was that because their programmable logic controllers and physical systems were disconnected from the outside internet, they were mathematically impossible to hack. Then, everyday operations began breaking that barrier. A maintenance contractor would plug in a laptop to run a diagnostic. An engineer would use an infected USB drive to update a piece of software. These early breaches were not targeted attacks against the factories themselves, but they introduced simple malware into the environment. They proved that absolute industrial isolation was an illusion, leaving critical infrastructure running entirely on blind faith. In 2003, that blind faith was tested by the SQL Slammer worm, a piece of code designed to exploit a vulnerability in Microsoft servers. The tiny worm spread across global networks in minutes, eventually crossing over into the corporate network of the Davis-Besse nuclear power station in Ohio. From there, it flooded the plant's operational technology environment, entirely disabling the critical safety parameter display systems operators use to monitor the reactor. The incident exposed a severe operational conflict. In a standard IT office environment, administrators can usually fix a malware infection by simply taking systems offline and rebooting the servers. Applying that exact same IT fix on an operational technology floor could unexpectedly shut down a continuous manufacturing line or risk a physical safety incident. Because operational technology environments must maintain continuous availability and strict physical safety protocols above all else, traditional IT security methods actively fail when applied to industrial hardware. 7 years after the Slammer worm accidentally disrupted operations, attackers weaponized that exact vulnerability. The 2010 deployment of Stuxnet marked the transition into an era of precision-engineered sabotage. Unlike previous worms that blindly copied themselves everywhere, Stuxnet was highly specific. Once it breached a facility, it actively hunted through the network until it found one exact piece of hardware, specific Siemens programmable logic controllers. It intercepted the communication lines between those controllers and the operators. While the malware commanded the machinery to tear itself apart, it simultaneously fed normal, healthy data back to the control room screens, blinding the operators to the destruction happening directly beneath them. By deliberately manipulating industrial logic to shatter steel and concrete, Stuxnet proved that code could be deployed as a highly targeted kinetic weapon. Attackers quickly realized if they could target an isolated facility, they could target the grid itself. In 2015, attackers breached the IT networks of regional power companies in Ukraine, eventually gaining access to the operational control centers. They took complete remote control of the operator workstations and systematically switched off dozens of vital electrical substations. Hundreds of thousands of civilians lost power in the middle of winter, demonstrating industrial breaches could scale to destabilize the services entire regions rely on. Then, in 2017, researchers discovered Triton inside a massive petrochemical refinery in the Middle East. This malware focused its attack on a plant's final layers of physical protection. Triton was uniquely engineered to attack the facility's safety instrumented systems. These are the autonomous fail-safes designed to instantly shut down a plant if pressures or temperatures reach critical levels. The malware's sole objective was to disable these emergency brakes entirely, leaving the volatile plant primed for a catastrophic industrial accident. Today's threat landscape has expanded to include nation-states and supply chain compromises that specifically target these last lines of physical safety. Because industrial systems provide the electricity, water, and fuel required for modern life, a breach of their safety protocols can have immediate consequences for the surrounding community. Plant managers can no longer rely on the assumption of an air gap, and standard IT firewalls are inadequate for protecting heavy machinery. This brings us to the International Electrotechnical Commission's 62443 standard. It is a defense framework developed to address the specific vulnerabilities exposed by the last 4 generations of industrial cyber threats. To prevent incidents like the slammer worm from crossing over from corporate IT, the framework dictates a specific spatial security model. It breaks a plant's network down into isolated security zones. These zones only interact through strictly controlled conduits, allowing a facility to quarantine an infection in one sector before it reaches the critical motors and pumps in another. By stacking these architectural boundaries with specific access restrictions and continuous monitoring, the standard enforces a defense-in-depth strategy that protects physical hardware without compromising the plant's operational availability. As digital attacks grow increasingly capable of manipulating physical infrastructure, IEC 62443 provides the technical requirements needed to secure modern industrial environments. We have established that standard IT security falls short in an industrial setting. Join us tomorrow for Day 6, where we will examine exactly why rebooting a bank server is fundamentally different from rebooting a factory floor. Subscribe to follow along with the challenge.
Welcome to the Cybersecurity Forum. Don't forget to subscribe to this channel and like the video. This is to get the latest cybersecurity news and updates. Stay secure with us.